Hello and welcome to mini lecture 15 on the chain rule. This is going to be the most difficult of all of our derivative rules. It is going to let us take the derivative of composite functions, so please take the time that you need to watch and or re-watch this video as you need. Alright, so first of all, a brief introduction or review of composite functions. So if we have the composite function f of h of x, then this means that we have some function h of x that has independent variable x and a dependent variable y, and then we're taking that dependent variable and we're plugging that into a new function f to get a secondary dependent variable z. So this is now our new independent variable, and the result, the composite function, is z equals g of x is equal to f of h of x. Note the mapping of the dependent and independent variables, so let's go through it one by one. So first of all, we have our independent variable of the inside function x is going to end up being the independent variable of the resulting composite function. All right. So what this implies is that the domain of the composite function is the domain of the inside function. All right, so this x is the same as that x. Similarly, if we take the dependent variable of this function is the same as the independent variable of the outside function, because we have to take this inside function and plug it into the outside function. So the thing that we get out here has to go in there. All right, so the result of this is that the range of the composite function, the domain of the outside function is the range of the inside function. Finally, we have that the outcome of the outside function is the outcome of the composite function. So the dependent variable of the outside function is the dependent variable of the composite function, so the range of the composite function is the range of the outside function. All right. Let's see how this plays out in two different biological examples. We might have the inside function minus x squared. This minus x squared gives us a value for y. We then plug that y into e to the y to get f of h of x is equal to the Gaussian function e to the minus x squared. All right. Or we could have the inside function ln of x. This gives us a y. We then plug that y into f of y to get f of the natural log of x to the fourth power as our composite function. All right, so the chain rule is going to let us take derivatives of functions like this g of x or like that g of x. So if we want to take the derivative of g of x, this is the derivative of f of h of x. Remember that with the whole inside function here is our independent variable of f. So we're going to take the derivative of f of h of x with respect to the whole function h of x, and then we're going to take the derivative of h of x with respect to x. So another way of saying this is, how does the outside function f change as we change the inside function, and how does the inside function change as we change our independent variable x? All right. So another way of writing this is that d by dx of g of x is the same as the derivative of the composite function is df of u du times dh of x dx. Now this u is a stand-in for h of x, and it just helps us realize that we can take the derivative of this outside function with respect to its independent variable, and then we have to plug in u equals h of x, because we want the ending result in terms of x. All right, so let's break it down. It's the derivative of how the outside function changes as we change h times how h changes as we change x, gives us how the composite function changes as we change x. All right, so in some ways we can think of canceling terms, so we could cancel this dh of x and that dh of x, and it will give us how the outside function df of h of x, that's g of x, how that changes with respect to x. So we can't actually do that canceling, because remember, you can't cancel these d's, but we can kind of do it in our brain to give us an idea of what's going on, and we end up with how this function g of x changes as we change x. All right, so in terms of derivatives, we're essentially saying what is the slope here? So we have a change in x leads to a change in y. And then we want to know, how does that same change y map to a change in z? And the ending result is how a change in x changes z. All right. So how do we do this chain rule? Please just, for now, let's just follow some rules, and then we'll see how these play out in practice, and you'll get the handle of it and get to figure out how to do it faster and more efficiently. But for now, just follow the rules. So the first thing that we want to do is we want to find the different subfunctions of that composite function. So if we have g of x is equal to f of h, or I should write it out this way, f of h of x, we want to figure out what f of y is and what h of x is. So we first need to define this function here and this function here. Then we're going to perform a change of variables, because it's really complicated to take the derivative of f with respect to the whole function h of x. So we're going to just do a quick change of variables to remind us what we can do. So we're going to define h of x equals u, and f of h of x is going to become f of u. So we're going to take this whole quantity here, and we're going to just say that u, and this gives us a little bit simpler expression for f of u. Then we're going to take the derivative, so we have d f of u du, and then we're going to change that variable back, so we have d f of u du, and then you're going to plug in, everywhere you see a u, you're going to plug in h of x. Why do we have to plug in h of x? Well, we want the ending result in terms of x. So if we have the derivative of f with respect to u, we can't leave this u in there. We have to substitute back in that u is a stand-in for h of x. All right, so then in the third step, we're going to take the derivative of the inside function, so d by dx, of the inside function h of x, and then we're going to multiply the two together. So we're going to end up with dg of x dx is the result from step 2, which is df of u du, substituting in h of x for u, times d h of x dx. All right. Now, let's see how this plays out in practice. It's kind of hard to write down the steps, but once you see it in practice, it might help. So let's think about how it works out in practice. Suppose we have the function g of x is equal to e to the x squared. How do we write this as a composite function? Well, one thing that we can do is we can know that this is a function in and of itself, so let's define this as h of x. And that means that we have f of h of x, where f of u is equal to e to the u. All right, so let's do the change of variables. We end up wanting dg of x dx is equal to d by dh of x of f of h of x times dh of x dx. Now, it's confusing to take the derivative of f of x with respect, or f of h of x with respect to that whole h of x. So we're going to do a little change of variables here, and we're going to say this is taking the same as taking the derivative with respect to u and plugging u equals h of x back in times dh of x dx. All right, so what's our change of variables? Well, we have u is equal to h of x is equal to x squared. Okay, so that was our first step. All right, now that we've done that change of variables, let's find this derivative here. So we want df of u du is the same thing as taking d by du of e to the u Now, remember that the derivative of e is the special case where this is simply e to the u. Now, I want to plug u equals h of x back in because I want the ending result in terms of x, not in terms of u. So I want this to be e to the x squared is df of h of x. dh of x is that. All right, so that gives us this term here. Now we have to do this term here. So we have dh of x dx is simply d by dx of x squared. Now we use the power rule, and this is 2x. To get the ending result, we take the product of those two things. So we have e to the x squared times 2x. And this is the resulting answer. Okay, so let's do one more practice problem. We have d by dx of ln of x to the fourth. Okay, what is our composite functions? We have f of u is equal to u to the fourth, and we're going to call this whole thing here u. So g of x is equal to the natural log of x. All right, so we found our outside and we found our inside functions. All right, let's take df of u du and then plug in u equals h of x. So first of all, we want to take the derivative of u to the fourth, and then we're going to plug in u equals the natural log of x. Okay, because we want the ending result in terms of x, not in terms of u. How do we take the derivative of u to the fourth with respect to u? Well, this is simply the power rule. So we have 4u to the third power, given that u is equal to the natural log of x. All right, let's plug that in. So we have 4 the natural log of x cubed. All right, so that is our derivative of our outside function. Now we need to take the derivative of the inside function. I'll write it out. dh of x dx is d by dx of ln of x. This is simply one of the other special derivatives and gives us 1 over x. To get the derivative of the composite function f of h of x, this is our ln of x to the fourth power. To get that, we take the product of this, and we end up with 4 ln of x cubed divided by x. And now you have taken the derivative of two really complicated functions that are actually the composite of two simpler functions. All right, so with that, I'm going to leave you with this self-study. Just remember, identify your composite functions, take the derivative of the outside function, and make sure you give the ending result in terms of the original independent variable, and then take the derivative of the inside function and take the product of the two. All right, see you in class.